Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Ryan French with us today. Hey, Ryan.
Hey, Frank. How you doing?
I'm doing awesome on this April 3rd of 2023 as we do this recording. And spring is in full swing in Phoenix. We're getting our spring winds today in particular. So we'll get some dust blowing around and all that kind of lovely desert orientated stuff.
Beautiful.
And I think you're more in the mountains, are you not?
Yeah, I'm up in Boulder, Colorado. It's felt a bit like spring the last few days, but I think we actually have some more snow coming this week. So this might be a bit of a fake spring that we're experiencing at the moment. So we'll see.
Fake springs, I love it. That's a pretty awesome poster you got over your left shoulder there, that Parker Solar Probe. Very nice.
Yeah, thank you. There's a few different sort of space mission posters scattered around my apartment here. My favorite one, although it's not as big, is actually the smaller one right here. So this is the sun on the day that I got married last year. But really excitingly, during the wedding ceremony, so during like the half-hour wedding ceremony, there was actually an X-class solar flare, which is the biggest class of solar flare, like during the ceremony. And I researched solar flares, so I had to get a print of that for the wall.
That is such
a lot of that stuff. Yeah.
That is such a great story. Well, congratulations on your marriage too.
Oh, thank you. Thank you.
Very cool. What's your position there in Boulder?
Yeah, so I'm a postdoc out here. So I finished my PhD last April time back in the UK at the UCL Mallard Space Science Laboratory. Yep. And then last summer, moved out here to Boulder, Colorado. So this is still my first year out here as a postdoc and loving it so far.
Well, congratulations. Very awesome.
Thank you again.
Postdocs, marriage, it's all great. Fantastic. And you already mentioned a little bit, but Ryan, what do you like to do for research?
Yep, so I'm a solar physicist. So I research the sun, the atmosphere of the sun, and probably more specifically the dynamics of magnetism in the solar atmosphere. So I've sort of ranged from the very largest solar flares, X-class solar flares, to very small sort of dynamic events, such as very small flares and even umbral flashes, which is what we will be talking about today.
Very cool. And that is going to bring us to this very awesome APJ letter. It's open access, people. Go get a copy for free. First observation of chromospheric waves in a sunspot by DKIST ViSP, the anatomy of an umbral flash. And Ryan, take us away.
Yeah, so first of all, I'll thank my co-authors here. So Tom Bogdan really was a pillar of this paper. He's retired now, but we essentially pulled him out of retirement to get his expertise in all things chromospheric dynamics. Roberto Cassini and Alfred DeWin also instrumental to this work. Roberto is the PI of the instrument that we're using data from today, and Alfred also pivotal in collecting and analyzing that data. And Phil Judge is just a very wise guy who knows a lot about everything and just gives amazing advice and insights all the way through, which continuously shake up the paper as well. So the dream team, and I couldn't have done it without any of them.
There we go. Great shout out. Very good.
Yeah, so I guess I'll jump in with the abstract. So first, I guess I'll talk a little bit about this instrument which we used. So the Visible Spectropolarimeter, or ViSP for short, you'll hear me use the acronym, which is at the National Science Foundation's Daniel K. Inouye Solar Telescope, or DKIST for short there. So DKIST is a solar telescope. It's got a 4-meter diameter. And to put that into context, that might not seem like a lot in terms of astronomical telescopes, but you get a lot of photons from the sun, right? Yeah, a lot more than distant objects. So with 4 meters, the amount of photons that you can get is crazy. And the previously largest solar telescopes had a diameter of 1.5 meters. So this is a big increase from there. There are 4 different instruments on the telescope. ViSP is one of them and measures spectra across a slit and rasters, creates sort of maps of spectra across regions of the sun. Okay. There's also a coronagraph on the telescope. There's an imager as well, which will take high cadence images. But here we're just using the one instrument. And this is actually data way back from the science verification phase. So this data wasn't originally intended to be science data, But during the science verification, we had this lovely small event called an Umbral flash, which I'll talk about in a minute. And the data was too good to not analyze. So the telescope now has actual science data, and people submitted proposals and have data. So there'll be a lot more coming from this telescope.
Nice.
But this is the first from the instrument from the science verification.
Very cool. Very cool.
Okay, so let's talk about. I might skip actually right ahead to figure 1 if that's okay with you.
Figure 1 looks good. Continuum image. Here we go.
Yeah, so just talking a little bit about what ViSP is and how ViSP collects data. So the image on the left, that full frame, is an image from HMI. So this is just continuum, white light continuum of the sun. We're looking at already a cropped region of the sun here. The X and Y axis are in arc seconds, and the sun extends to about 950 arc seconds to approaching the left edge of the sun here. Okay. And then this black box zoomed in even further is the field of view of ViSP. And you can see that we're focused here on the top of a sunspot. Nice. And the way ViSP works is it has a horizontal slit, and it measures spectra all along that slit in 3 different wavelength windows. So in this case, we're actually looking at one window is looking in the photosphere, looking at iron 1. The second window is looking in calcium H, which is a chromospheric line, so a layer above from the photosphere. Mm-hmm. And then the third window is another calcium line, which again is a different layer of the chromosphere. Okay. And the way this works with the single slit, and it moves the slit down incrementally to build that image. Nice. So as a result of this, you can imagine you're moving your slits. So when you create your map of, the sun, you're sort of combining spatial information, but also you're adding in temporal information as well, because the sun might change slightly as your slit is moving across the sun. Okay, cool. The frame on the right that I show here, this is the same region, but this is an image of the sun's corona from the atmospheric imaging assembly. And what you might notice is a small solar flare there. That's that bright region. You can see some loops. That is a solar flare. It's a C-class. It's not massive. We don't think, in this analysis, we don't think that the solar flare has anything to do with the waves that we see. But we include that here, as a sense of completion, because some people might disagree with that. So we just, for all cards on the table, we say, hey, there was a solar flare here. We don't think it's related, but if you think it is, go investigate that. And returning back to those long horizontal boxes, the 2 vertical dashed lines, that sort of highlights the field of view that we will actually be looking and exploring in this article. You can see to the left of that, to the right of that, there's a whole lot of nothing. All the interesting stuff, the sunspot, is there in the middle. So maybe if we fast forward to figure 2, that's good. Just to show an example of some ViSP observations.
Let's get the full picture and we can zoom in as need be, and there we go.
Nice. So what we do here is we take a vertical slice across the maps from ViSP. Okay. So now each point on the y-axis is a different slit position. Okay, so they're taken at slightly different times. Mm-hmm. And then on the x-axis, that is the spectral information, so your variation in wavelength. Yes. And what you can see here already, just from looking at these original plots, is we've got some incoherent or some structures that are changing, right? We can see in the top left, those little dark blobs are sort of reappearing, and we can see that across all the images here. Yes. And what I will say, and I don't know if everyone watching this is familiar with spectropolarimetry, but as well as just taking spectra, right, in intensity and looking at the variation in wavelength of intensity, which gives you some things like Doppler velocity and line width and stuff like that. Yes. We can also measure different polarization states of the line to also calculate or measure the Stokes parameters. So Stokes Q, U, and V, and I is just regular intensity. And these can reveal further information.
Yes.
Primarily relating to magnetic information in the field of view of this map that we're creating. Now, historically, when looking at polarization measurements of the sun, It's fairly easy in the photosphere, the lowest layer of the solar atmosphere. There's a lot of photons coming from that layer, and magnetic fields are very, very strong. So it's very easy to see signals of this magnetic field. But when you're up a bit higher in the chromosphere, where you don't have as many photons, the magnetic field is weaker, it's harder historically to be able to measure directly what the magnetic field is doing and to be able to measure polarization measurements. Okay. But lucky for us, we have a 4-meter solar telescope. So we are able to do that here in a way that we haven't really been able to do before.
Cool.
And what I will mention before we go on to the science is because these were the science verification observations, the telescope hadn't fully finished calibration and pipeline processes and stuff like that. So there was actually a slight defocus on 2 of the cameras that are looking in the chromosphere. So because of this, the lines are broader than traditionally, or broader than they are in reality. So because of that, we don't do a full spectrophotometric inversion. We go old school a little bit, and we resort to fitting Gaussian lines. And you can see in the examples on the bottom row here that it works pretty well. Gaussians to the very center of the emission line, it works. And so we're able to pull out information without doing any complex inversions, which is good. Yeah.
It's nice. Very good.
Okay, let's go on then to figure 3, I think, which is where the good stuff starts.
And if you forget what your polarizations are, there you go. Equation 1 and figure 3. Okay, here we go.
Cool. Okay, so I will go through some of these panels, which sort of cover some of the text in the previous page as well. But essentially, these are all of the parameters that we're able to pull from the spectra for that little field of view over that sunspot region. The top left panel, this is the photospheric line. So this looks similar to that continuum image that you saw. You can see you have the dark sunspots. That center, well, the whole thing's actually a sunspot. That central region is the umbra, which is the center of the sunspot. And that outside region, which is not quite as bright as the very edge of the frame, that's the penumbra. So that's still part of the sunspot region here.
I'm with you.
And this is the photospheric line, iron 1. You can see intensity measurement. You see the sunspot. On the right-hand side of the top row, this is the Doppler velocity of the same of that same region. So this is photospheric Doppler. Now, we actually had a bit of trouble choosing a reference wavelength to calculate the Doppler velocity. When you calculate Doppler velocity, you need like a reference point, right? You need a stationary point that the velocity is referenced to. What we did, thankfully, in the window of the iron 1 spectral line, there are telluric lines, which are lines in the spectra that come not from the sun, but actually from the Earth's atmosphere. And the Earth's atmosphere is stationary on average, right, over your sort of your viewing point. So you're able to say for certainty and use that as a reference wavelength. So that then confines the rest wavelength of the sun, which is great. And then on the photosphere of the sun, and then for the chromosphere, we actually took in the window of the calcium 2 line, which we look at in the rest of these panels, there's a very small photospheric line, which you were then able to align with the photospheric line in iron 1, and then we're able to get reference wavelengths for Doppler velocity for everything. So we're able to confidently say these are the true velocities of the plasma on the sun, and don't take into account, solar rotation. We're near the edge of the sun, so none of that is a problem. So this is all plasma velocities, which is very, very great.
I'm with you. Very good. What are the blue and red vertical half dash lines?
Yep. So these lines that feature all the way through these panels, these are the locations that the regions of interest, and we'll take cross sections through these. The previous figure we actually looked at, where I showed a cross section, was actually taken in one of those vertical lines. And the next figure, which we'll talk about in a minute, also looks at these regions. That's sort of the region of interest.
Got it. Cool. Okay.
Yes. So let's then move on to row 2 here. So this is now looking at a spectral line, the one that we primarily look at, calcium 2, or it's one of the lines of the calcium 2 infrared triplets, as they're sometimes known. And we show intensity here on the second row on the left. And for sort of context, we overplot the position of the sunspot in the photosphere, just for context, so you sort of know what's happening. You can already see, even though you're not that far above the photosphere, things are already looking very different here. Your magnetic field and your plasma is sort of expanding away, so you don't have that super defined outline of an umbra. You now have something that's a bit more, not quite as defined on the edge there. And what you might notice immediately is sort of in the center left of the image, or even down to the bottom of the frame, these horizontal white ridges.
Right, like waves.
Like waves.
Waves.
No spoilers, yeah. And you'll notice these aren't really in the photospheric lines. They are here in the chromosphere.
Yeah.
And we see them in all the parameters. So very striking on the Doppler velocity on the second row.
Yes.
So this is now a Doppler velocity up in the chromosphere. You can see these ridges very clearly in, they're very clear there. And you can even see there, it looks even more wave-like because you can actually see there's redshift and blue shift across the ridges and crests of the ridge structures, right? Which is really interesting. Yes. And I'll just point out, there's other stuff happening to the right-hand side of the frame. You can see that area of redshift there. That is interesting to some people, I'm sure, but not what we're focusing on in this study. We're looking at these ridge-like structures and what's going on there. So line 3 on the left, this is line width. So this is the width of the emission line. Okay. And again, it's a bit more subtle, but you can still make out in the same location some ridges here.
Yes.
And you can actually see sort of the bottom 2 ridges, which are just above. You can actually see the very sharp transition from sort of white to black, just there where your mouse is. Just there. Yeah, that one and the one above as well.
Yep.
And we will see these in the next figure, and they are very interesting. But I won't get ahead of myself here, but you can see it in the images, that sharp transition from white to black. And then in the remainder of the frames, these are now the polarization measurements. So the azimuth and P, which we're labeling P, is linear polarization. These are both related to linear polarization. So these are related to sort of the orientation of the magnetic field in the plane of sky. So it's not related to the strength of the magnetic field, but it's related to the orientation both in the line of sight and the plane of sky. So variations in azimuth, you can see are more subtle, but you can see there are some ridges here still. Yep. And in linear polarization, the bottom left, really clear, these ridge-like structures as well, really clear. So already we're now being able to say these waves, or whatever they are, right, no spoilers, are not only happening in the plasma itself, right, in forms of the line width and the Doppler velocity and the intensity of the plasma, but it also relates to the magnetic field as well, whatever this is.
Cool. Good.
And then the bottom right panel, this is related to circular polarization. So where it says B loft, so the panel just above, that one here.
This one?
So this is measuring the line of sight magnetic field, so B line of sight. And again, we're seeing there are some subtle ridge-like structures here in the line of sight. So this could either be due to the changing magnitude of the magnetic field, right? But because we're quite close to the limb of the sun, this could also still relate to the changing angle, because if you change the angle, you're also going to change like the line of sight component of the field, right? So you can't say with any certainty whether or not this is actually a variation in the strength of the field or just the orientation of the field.
Oh, let me ask a question here, since you mentioned it. What is the total elapsed time over which the observations are made? Is this done over one month, 1 minute?
Excellent point. Yeah, excellent point. I sort of glossed over that by missing the first page. So the slit starts at the very top, right? So it's a horizontal slit. So it starts at the top of the frame. Yep. So you have a horizontal line, and it takes 38 minutes to go all the way down and get to the bottom.
Got it.
So that works. There's 300 sort of pixels going down. So each time step, there's like a 7.8 second delay or something between each time step. And what this sort of does is gives a projected speed of the slit. So the slit sort of moves across the sun. It's a speed of about 3.8 kilometers per second.
Okay,
Yeah.
cool.
Yeah.
Thank you.
Yeah, so that is crucial when we start to think about what we're actually seeing in these figures here. So to make sort of it clear to the point that these aren't images, these aren't stationary in time. The y-axes you can see I've plotted both in terms of physical distance and actual time as well. So axis, yeah, so that goes from 0 to 2100 or 2200, whatever that is there. That's the 38 minutes from top to bottom. So
very good. Okay.
What we could be seeing, right, and just from this map alone, we wouldn't be able to tell the difference just from this map, whether we're seeing a wave structures that are sort of moving across the sun like that, and we're sort of seeing the ridges of these things that are sort of moving, say from top to bottom or bottom to top, or if that whole area is sort of pulsating towards you and away from you. And then as your slit moves over the area, you're sort of seeing in some places you're seeing when it's sort of compressed and one when it's not compressed.
That's fair enough. Okay.
Yeah. So you can't tell which of those two just from these maps you're looking at.
Right.
So I think it might be the next page, which has some nice equations. Yep, here we go. Equations 3 and 4. So we don't need to go into the specifics of this, but basically this is an expression of what we are calling like an induced Doppler effect. So it's not Doppler in the same way that we talk about Doppler motion in the line of sight, right?
Right.
But if you imagine, it's a different sort of Doppler.
Yes.
So if you have waves going across like this, and your slit is going across like this, so going like this, and your slit is coming across, the actual wavelength that you observe will be different to the true wavelength of that wave, right?
I'm with you.
It's a difficult concept to sort of wrap your head around, I think.
Yeah, you're told.
But if you can sort of, if your slit was moving in the same direction as the waves were moving, you'd extend the wavelength of those waves in your image, right? But if you're moving the other way, because you're moving against the direction, you're going to observe sort of the wave crest to be closer to get, it's going to be compressed.
Yep.
So, and this just formalizes that C is what we're calling sort of the wave velocity.
Okay.
So the wave velocity related to the slit velocity, so the motion of the slits, and also sort of the actual observed periods that you see as well. So it is possible if you know the slit velocity, which we know the slit velocity, right? We know the observed sort of separation, okay?
Yes.
We know the observed separation of the ridges, both in space and time, right? Because we've got that sort of raster effect. So if you know either the true wavelength or the true periods, you can calculate the true velocity.
Right.
And if you know the true velocity, you can calculate the true period.
Cool.
So is there a way which we can determine one of those two things? Yes, thankfully there is. So we don't show the figure here, but there is an instrument in space called the Solar Dynamics Observatory, or a telescope in space called the Solar Dynamics Observatory. This is talking about this paragraph on the bottom left here is what we're talking about here. And it has an instrument called the Atmospheric Imaging Assembly, which images the sun in multiple different wavelengths of light every 12 seconds or something like that. So this is the paragraph just to the left of you there.
Okay.
And what we see in AIA is a sort of coherent region of this sunspot. It's sort of pulsating, or we see intensity pulsations. And these intensity pulsations have a period of about 3 minutes. Now, 3 minutes is a very special period on the sun. It's like it's basically the fundamental frequency of plasma in the chromosphere. So if you hammer this chromosphere with, a solar flare, we have a solar flare, or the umbra is, have flux emergence and you're exciting the plasma. Any way you sort of trigger this plasma, it's going to naturally oscillate at this 3 minute period.
Gotcha. Cool.
Now, the reason this is useful, right, is because we see this 3 minute period in AIA, okay, in the center of the umbra. When we actually look at the period of the wave sort of the ridge to ridge separation in
Okay.
ViSP maps in the figure above, we see that it's 3 minutes. So what this tells us is, and if you could just return to the figure on the page above.
Yeah, I was going to say, yes, let's go back
is,
there.
Yeah, these are not waves that are sort of moving across the sun. So we're not seeing top to top. We're not actually seeing, waves moving like that. This is a plasma that is sort of pulsating towards and away from us.
Cool.
And then as the slit moves over that, we manage to see these ridges.
Very nice.
Now, when you think about it, it's therefore lucky, really, it's luck, right? That the speed in which these waves are moving towards and away from us
right.
are like comparable with the speed of 3.8 kilometers per second that the slit is moving across the sky.
Yeah.
Because if it was moving too fast or too slow, we would see almost like a snapshot or a blended version of this and wouldn't be able to pick out the actual variations in the magnetic field and the Doppler velocity across these ridges.
Right.
So a stroke of honestly luck.
Fortuitous is good sometimes, right?
Fortuitous, certainly.
It's kind of like, having a big X-class flare when you get married or something.
Yeah, exactly. Yeah, maybe I'm just a lucky guy. I don't know. So therefore, what are these ridges due to? Well, I mentioned we have these brightenings that we see in the extreme ultraviolet observations that we see here. Is actually something called an umbral flash.
Yes. Okay.
So umbral flashes, they are dynamic transient features that exist in the umbra, the center of sunspots. This one lasts an hour, which is fairly typical. And they oscillate with this 3-minute period. And yeah, they have been observed for many, many years, sort of oscillating with this 3-minute observation. But this is the first time that we have, at least with this much signal to noise, have magnetic field information of this umbral flash. And as we will see sort of in a little while, we will see that we're able to put together a very nice picture of how umbral flashes work based on these observations.
Okay.
So just before we move on to the next figure, if we could just return to the figure above, and I'll just point out those vertical dashed lines again. So we have these 2 vertical dashed lines. One is cyan, one is magenta. We have them in all the parameters here. And yeah, so if we could then move on to the next figure, which I believe is figure 4, we're then going to take basically cross sections sort of along these dashed lines. So to look at in a single sort of Y position, single X position, how these parameters vary in the Y-axis, essentially.
I'm with you. Figure 4, umbral flashes. Ooh, there we go. Okay,
so now we have some very nice wave shapes here.
We do.
So top left is intensity. So you can see here there's the cyan line, the magenta line. They were fairly close together in space. You can see in intensity, there's not much difference. In some of the other parameters, there's a bit more difference, but we'll talk about them. Intensity, very simple. We have these sort of horizontally symmetric rise and falls of the intensity in time. And you'll notice in this plot, again, the very top axis it shows the variation in space, and then the bottom axis is time. So again, these are variations we are saying they're variations in time, but in terms of, as far as our raster is concerned, it's also variations sort of in space, because it convolves the two.
Yes.
But as far as we're concerned, these are variations in time more so than space.
Okay, good.
But yes, in intensity, top left, you see there are these very symmetric rises and falls. And then compare that now to the top right, the Doppler velocity. Now you're seeing something very different, not symmetric at all. We have these sort of shallow rises and these steep cutoffs, and then these shallow rises and then steep cutoffs. And you can see the last two, which were the brightest in the frames above, are the 2 most dramatic here. Now, already from these sort of shallower rises and steep falls, this already starts to tell us maybe we're looking at the S word here, shocks, right? So shocks, you don't want to call the word shock if you can't back up the word shock, but maybe that word starts to sort of get in your head here that maybe you're looking at a shock. And you can also see it's important to note in the Doppler velocity, remember, these are true velocities. So 0 is rest plasma.
Yes.
So you can see we are moving from plasma,
Bang,
which is
bang.
Yeah. So positive Doppler velocity is redshift. So if it's above 0, it's moving away from us. If it's below 0, it's moving towards us.
Okay.
Yeah. So you can see there's plasma, which is, starts to accelerate back towards the sun, and then all of a sudden it comes back in our direction again and starts falling back towards the sun.
Very nice. Very nice.
Now, the second row, this is line width. And if you remember from the maps on the previous page, there was that very sharp white to black that we saw in those ridge features.
Right.
And you can see that very clearly in the right two of the oscillations. So the right-hand side of the figures here. So you get the two most dramatic ones. If you go all the way to the right, left panel, but a very sharp Z. Not quite. So the right-hand side of that panel.
Over here.
Yeah,
there we go. This one, this feature.
Yeah, okay. That one here, yeah. You can see very dramatic shift from a very small line width to very large line width. These plots, by the way, they've been detrended from the overall trend just to show the actual variation of these shock parameters.
Okay.
Now, that's strange. Exactly where your mouse is, a sudden drop in line width and sudden increase in line width is something that we actually didn't fully manage to explain, but is a clear sort of example that there's some non-linear effects here in this way. The fact that we're seeing this, so we don't fully we have some
mysteries,
possibilities, which we say it might be this, but that is an ongoing mystery apart what causes that sudden drop and increase in velocity.
Mysteries are good.
Mysteries are good. But for the remaining frames, we are going to focus the equivalent point of where your mouse is. So these so that shock there and the one previous, where those last two dashed lines are. Yep, that one and the one after. These are the strongest two of the shocks. So in the other parameters, the ones which maybe are a bit harder to observe, the polarization parameters, we're looking primarily now at the strongest two shocks where these signals are strongest.
Yes.
So in the second row right panel, so this is now looking at the azimuth, which is related to the linear polarization. You can see at the shock positions, it's a bit noisy beforehand, but we see in both of these positions, that's why we include two cross sections here. So you can say, okay, it's not just chance that you see it in one. We can see those reductions, those drops in the azimuth there. Yep. So there and there. Exactly.
Yep. I'm with you.
And similarly, the third row left panel, this is linear polarization again. These are a bit clearer. We can see the oscillations a bit better going across, but in particular, those last two are very clear, again, reduction in the linear polarization.
Yes.
The panel to the right of that, the line of sight magnetic field, is the noisiest of all the parameters. It's the hardest to observe, but we think, at least in the magenta line here, we're seeing very clear evidence that the magnetic field is dropping at these shocks. And you can also see it just at the very edge of the frame. We sort of stop the observations mid-shock, but you can see right at the end there's a reduction there as well.
Yeah, right here.
So we see sort of three of them.
Bang, bang, bang. Cool.
And interestingly enough, the bottom row here, these are looking at the other lines. So that's the iron one, the photospheric line. We see some oscillations, but with a different period. And this is expected, right? Because we're not looking in the chromosphere. This is the photosphere. We don't really see the 3-minute oscillation in the chromosphere. Instead, we see something else, a 5-minute oscillation. And on the bottom right, this is another chromospheric line, which we haven't really spoke about. We just have intensity for this line, for this analysis. And we see, again, these observations of the oscillations in intensity in these lines.
Very cool.
So the question is, what is happening? And the final sort of clue to the puzzle to start to put together an explanation of what is going on before we dive into the quantitative stuff, just a qualitative explanation. If we go to the figure 5.
Let's go to figure 5.
We basically return here. Let's look at the bottom two panels here. Let's ignore the top panel for now. So these bottom two panels, these are looking at the Doppler oscillations that we showed before. for the magenta line and the cyan line, so two very close points in space.
Yes.
And what it's important to know is because we're transitioning from blue shift to red shift, is to actually figure out this plasma that we're seeing, is there a net motion towards us or a net motion away from us? Like it sort of matters in this interpretation in terms of what's going on. So what you can do fairly simply is you just integrate under these curves.
Okay.
So you can see when the cyan curve first crosses 0, the plasma moves up for 20 kilometers before moving down for 51 kilometers, and then it moves up for 10 kilometers, down for 83 kilometers, and so on. And what we have across the full sort of umbral flash, right? And we're only seeing about 10 minutes in this hour of the umbral flash. Okay. But in both cases, there is a net upwards motion of plasma. So if you add up all the numbers on top, all the numbers on the bottom, you see there's a net blue shift, which is an upward motion of plasma. Okay. But clearly here in the shocks, where the shock is, there's a very strong downward motion of plasma. Yeah. So what we can paint a picture on by combining this, again, very clear signals here. And the only reason we can see these shapes so well defined is because of the amount of photons that we've got. Signal to noise is incredible from this telescope. Awesome. So the picture that we're painting is you have plasma that is rising up. Okay, plasma is rising up. There's remember, your plasma here is in sort of a tube of magnetic field. Okay. And what happens is your plasma suddenly collides with plasma that is sort of stationary above it. So it collides with that, and then all of a sudden, that's your shock, a sudden de-acceleration, and then your plasma starts to fall again. Yeah. Okay. Then as it starts to fall, suddenly you have plasma coming up from below, which hits your plasma that is now falling, and that is sort of the plasma that causes the shock for the plasma below, and sort of pushes that plasma to start to move that plasma up again. Right. So this is an interesting picture. We have the net motions, we have the increase and decrease of the velocity, we have that weird line width as well, which might be due to heating at the positioning of these shocks where that plasma is suddenly being compressed. Okay. But we also have the polarization measurements to back it up as well. Yeah. So if you go up again to the previous slide, we see that drop in magnetic field. So that drop in magnetic field is likely as your tube of plasma of your magnetic field is rising up and hits that shock. Your sort of flux tube sort of expands as you sort of hit that stationary object. Your flux tube expands. So if your area of flux is expanding, your actual magnetic field strength will decrease, right? Because you have conservation of flux. So now imagine the picture that we're sort of painting is along this tube of flux. You have these sort of areas of increasing, the area of the flux tube decreasing, and your plasma is moving up and down as this happens. So this is a nice little picture that we think is a great little picture to come out of these first results from the science verification observations of the telescope. Indeed. But with that considered, with us confident that we're sort of looking at shocks, we can take it a little bit further and start to look at some sort of actual quantitative shock analysis too. Okay. So I think that's back on the previous page. Okay. I believe, if I recall. Yeah. So I won't delve into this too much. Again, this was intended as a first look at these results. We can't do full inversions of them, as I mentioned before, because there's that slight defocus of the camera. So we're not doing full analytical numerical solutions here. This is just to get an estimate of what some of these values might be. Exactly. Good. So we use these equations, which are called the Rankine-Huguenois relations, and I probably butchered that pronunciation here. Oh, good. And these can basically, you can use this relationship to calculate some shock values in plasma. Yep. It makes some assumptions. So first of all, it's assuming a uniform magnetic field, which we know we don't have. And it's assuming like an infinite plane parallel. And again, so this is idealized, not what's happening, but can give us some good estimates here. Get you a good fraction of the way there. Okay. Yeah, exactly. So by plugging in everything that we know, right? Yeah. So by using the net upward, like the average upward motion of the plasma, by taking into account the velocity of these shocks as well, then we can plug those values into those equations. the only sort of unknown parameter that we have to plug in is this gamma, which is the ratio of specific heats.
Yes.
There's a few different values that could be depending on how many degrees of freedom you would say are in this plasma. So, and actually the top panel that we can see poking up there actually shows the value for different sort of gamma values. So you can see the Mach number doesn't change that significantly. This just shows the Mach number of the shock versus different gamma values.
Yep.
So not a lot of variation, right? You're looking at
yeah, not huge, right?
What's that, from 3.1 to 3.7 on the very left for the smallest sound speeds, and then for greater sound speeds, that difference decreases.
Right.
But by making an assumption of what that might be, if you return back to the previous page, we can then get some, sorry, that page you're just on the bottom, scroll down here to those numbers.
Here?
Up a little bit. Yeah, oh, so we're looking at the top of the right-hand side of text. So we're able to calculate some parameters for these shocks. So a Mach number of 2.1, right? We have a actual sort of sound speed here of 9.3 of the actual plasma moving. We have a ratio of densities in front or behind the shock of 3.8, density of pressures of 4.6, and the density of, the ratio of temperatures of 1.2. So these are sort of standard values that you might think of looking at in a shock in front and behind of the shock. And in the magnetic field, we find sort of the change in the magnetic field to be about 10% across the shock as well.
Okay, and about 500-600 Gauss. There we go.
Yes, yeah. So these numbers are reassuring when you compare them to sort of larger statistical studies, which don't have sort of the signal to noise to look at a single shock with as much precision, but can look at a number of different shocks with maybe less signal to noise. The temperature, pressure, and density ratios they find are around what we in the range of what we find. Cool. In fact, I think we cite a study, I can't remember the lead author, where they find the values are from this range to this range, and they give that range for all these parameters, and for all those parameters our estimates are within those ranges, which is always good to hear. Always good to
comforting. See. Indeed.
Always comforting. Yeah. And I've recently been chatting to somebody as well who saw this paper, was interested in this paper, and is actually doing some numerical simulations of similar shocks to these, and they also have similar values too. So maybe there might be some interest in doing a comparison to numerical simulations rather than these more simple calculations here.
Cool.
So I think that takes us down to the conclusions then.
Yeah, very good. Very nice. Enough with some conclusions.
Here we are. Yeah. So that was all discussion we were just speaking about there. Two main findings, or the exciting things. Number one is for this umbral flash, we're able to measure it with unprecedented signal to noise, gives us these lovely Doppler profiles, and also gives us measurements of what the magnetic field, or hints of what the magnetic field is doing here as well. And so by using these observations, we can do two things. We can paint a qualitative picture of what this umbral flash formation mechanism looks like, but also calculate some parameters for what the shocks are doing as well, which are in agreement with other literature too.
Good. Very good.
Yep. So that's the work.
That's awesome. That is very, very cool. This is a lovely article. Very nice. And Ryan, thank you so much for walking us through this opening observations. And it's just there in the title, and you mentioned it kind of a couple of times. So let me push a little bit. And where do you think we go with this topic over, let's say, the next 2 to 5 years? There's clearly going to be some more observational data. Are there other telescopes that can help in? Is there more theoretical work? You mentioned a little bit of people doing more full inversions. It's just sort of, where do we go over the next couple of years on this topic?
Yeah, so as I mentioned before, this is the science verification observations from one instrument, the ViSP instrument, on the Inouye Solar Telescope on DKIST, right? Since the science verification observations, the instrument has only got better, right? They fixed the spectral defocus, so we can expect better spectral resolution, so you can do full polarimetric inversions of data sets like these as well. Other data exists in the community now. So the first call of proposals, observations were done, people are with data, and they're now taking the second call of taking observations from the second quarter proposals now.
Yeah.
So it's,
Nice.
I don't know exactly what the full range of data that is out there right now, right? But I have no doubt that there are other observations of umbral flashes and chromospheric waves currently sat on people's laptops,
Right.
which
Yeah.
people are probably analyzing as we speak. And that's just from the one instrument. If you combine that with images as well, high resolution images from the VBI instrument on DKIST2, you can take things to the next level also.
Nice.
So what's next? I expect a lot of exciting things to come from DKIST, both in terms of this small subfield of chromospheric waves, but also solar flares, quiet sun studies. It's an exciting time to be in solar physics with DKIST and Parker Solar Probe and Solar Orbiter and all these other fun things.
Cool. Well, I really look forward to seeing this topic move forward. We know a little bit more about the sun in a couple of years. Very cool. I look forward to your next article.
Thanks a lot.
Very good. Awesome. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.